Good evening. So we will continue with the synthesis steps where we have the designs and we want to generate the power area and timing reports and the netlist. So basically we are doing the front end VLSI design where we want to convert this into a netlist which eventually will go for back end VLSI design where the floor planning, layout, placement, all that will happen. So we have this design already. We will try it for both the designs that we saw. We'll look at it for this design and we will also look at it for the shift register design. The steps are identical, but because synthesis doesn't really matter much if it is combinational or sequential, the steps are almost the same. Okay, so we will start from a fresh terminal. We'll close the folder in which this thing is there. So for these experiments we need one more set of files which are available in another folder called as Cadence Digital Labs. It's inside the root file system. Inside that there is a folder called database. Inside the database there is a folder called Cadence Digital Labs, and inside that solutions. So this is the path for the folder which is called as this RC Labs. So you will see that here. Just right click on it, copy the whole thing, okay, and okay, so start from the beginning. Okay, it's there inside this folder. So copy that and paste it here. Okay, the RC Labs, the full folder. Now this folder is very important from a synthesis perspective. It's not required for simulation. So in the test or on the exam, if the question is saying simulation, just have to do the simulation part. You don't need this folder. Okay, so let's look inside this folder. This in turn has these four folders inside there: RTL, TCL, work, and library. Library folder is a folder which will have some library files. Okay, what is the library? This is the library that is going to have the description of all the possible gates, okay, which can be used for the generating the netlist. Now you can open this file. It's just a text file. It's a very large text file, but if you go down it will have lot of information about the gates in terms of the rise time, fall time, power consumption, area, and all those details. Okay, and this particular file is related to some particular technology. For example, here you see TSMC 090. Okay, so TSMC 090 is a technology file. So maybe this is a 90 nanometer technology file. Then you see here, okay, so this is the name of a cell. This is the name of a particular cell, and there will be some information about the cell area. Okay, pin. This is a layout. So there is a front and a back. Suppose you are connecting two pieces together. The front of one has to be connected to the back of another, means we have to know which is the front, which is the back, right? So all those details are here: direction, input, and all the details. So let us scroll down, see if we can find a NAND gate, for example. Okay, so there is something. So there is a NOR gate. So NOR, two input NOR gate, and this basically is the details of the NOR gate that we can use. Now this is going to be part of the netlist. All the cells here can be used for converting your full adder design into a netlist. So full adder might have some complex functions. Full adder is pretty simple, but if you look at the shift register, right, what is the always gate? There is no gate called as a always gate. So how do you convert it into a actual netlist. That has to happen through the synthesis process. It will eventually get converted. This always statement here will get converted into some gates inside the library. So that is the library folder. Here in this example, there are two example libraries. One is called a slow high VT library, another is called as a slow normal library, and we don't need to change or touch this at all. Okay, leave that alone. Just wanted to show you another folder which is very useful is called RTL, and as the name suggests, we write Verilog code in the RTL level. So all our Verilog code has to come inside this folder. This is very important for synthesis. Okay, all the Verilog code that you want to synthesize, you have to put it inside this folder. So how do we do that? We have the full adder open, right? File, save as. Okay, now I will choose this RC Labs RTL, save, shift register, file, save as. Okay, RC Labs RTL, save. Now if you see inside that, along with these two files which are already there, my shift register and full adder are also there in the same folder. So now we can start the synthesis steps. Okay, sorry, one more step I want to show you. So another folder that you need to do some work is the TCL folder. So library and work you don't touch. Okay, don't have to change anything there. RTL folder, here you have to put your RTL code, that is the Verilog code. TCL folder, now TCL is scripting language called as Tickle. Okay, so this Cadence RTL compiler tool that we are going to use, it doesn't understand English. Okay, what it does understand is the Tickle language. So this file that you're seeing here is a script or a file in the Tickle language, and this is the only way we can give inputs to the RTL compiler. We want to tell it to do certain things, right? How do we do that? We have to do it in terms of commands in the Tickle language, and this is a set of basic setup commands. Okay, now in this file, two lines are very important. First is this one. Okay, this is telling set file list, and we don't want to synthesize serial adder or shift register. We want to synthesize fa.v and shift underscore register, which is my shift register file .v. These are the two things that we want to synthesize, and you can give this one at a time. Let's in fact just not do two, let's give only one. We want to first do full adder, right? That is the first thing. Now the second thing to change is this line, set design. Here you have to give the exact module name that you want to synthesize. And if you have multiple, like if you have a hierarchy of modules, you can still give only one module for synthesis. And in that case, it should be the top level module. So for example, if you use this full adder to create a 4-bit triple carry adder. Okay, now that's the module name that you have to write here. And in terms of the files, you can either put all the files, all the modules in the same file, or you can put them in separate files. If you have separate files, you have to put that name also here. Okay, so this is the two things you have to change inside the TCL folder. Make the changes, save it. Okay, then we are done. No other things to change. How do you start the synthesis? Very important step to remember. Open this RTL folder. Here, open in terminal. Where do you do open in terminal? Inside the RTL folder where all your Verilog code is. Why you're doing this is because a lot of the commands that we want you to just remember, they are given relative to the RTL folder. So they will work properly, or they will work only if you are inside the RTL folder and giving these commands. If you are not in the RTL folder, okay, in that case the commands will not work. They will give you an error message and you will be going ahead with the next series of commands, but none of them would have worked. Output will not come. Okay, so remember the starting step for the synthesis after all this thing has to be from inside the RTL folder. Then our first steps always the same: csh source slash home cad CSHRC, enter. Welcome to Cadence. Once we see this, we know that we can start off with the commands. So here we start off with the first command, RC space minus graphical user interface or GUI. And then the tool will open up and we can continue with the remaining commands. Okay. So these commands are there in the manual. The same things we are going to type here also. So this is a GUI window which we will minimize for now. And now we are inside the RTL compiler tool. Okay, we are not in the Cadence environment anymore. So commands like ls and all will still work, but this is inside the RTL compiler. So ls will not give me my shift register.v. I can't see all those files. It's somewhere else. Okay, so now we have to start the synthesis process, and we will start with the first command, include dot dot slash tcl slash setup dot g. And this is why we tell you write it from run the terminal, open in terminal from inside the RTL folder, because this path that we are giving, okay, is correct only if you are inside the RTL folder. If you are not inside the RTL folder, then this is not the correct path. Okay, it will not find the TCL folder in the correct place and it will not work. So remember to start it inside that and then type this and press enter. Okay, so this is basically the setup.g file. Okay, it is running each of these commands separately, and it is doing whatever needs to be done. But main thing is it has taken these two: what is the library, what is the file, and what is the design. So that is the include tcl setup.g, just some setup information for the tool. So once that is done, we can give the next command, include dot dot space, sorry, include is done, set attribute library. Okay, dollar library. What is this dollar library? Dollar library is nothing but a variable that is defined here. Okay, so this library is here. Dollar library will basically take these two things for the variable library and press enter. Okay, so you'll see lot of messages and you should see all those messages, and then once those two are done, we can read the HTL code. So in the previous simulation also we had three steps. There was the Verilog, there was the elaborate, and there was the simulate. Here also is the same three steps. The first command that I'm going to type now, okay, which is read underscore HTL. This is the compiler. This is going to read your HTL, and if there is any errors in the Verilog code, because for example this will not happen in a practical setting, but in the exam setting, if your experiment is synthesis, you will write the Verilog code and go directly for synthesis. So there might be some problems in the Verilog code. If there are any errors, it will show you at this point. Okay, so I will show you, for example, fa.v. Let me forget a colon and run it. Read HTL dollar file list. What is this file list variable? This is again inside this setup.g file. So it knows that file list means I have to read the fa.v file and enter. And it is giving me a error. What is the error? It's giving me expecting colon found input. So I have to go back. Okay, make the change, save it, run it again. Okay, you don't have to start the process again, just correct the file and read HTL again. Okay, and then what is the second step in simulation? Elaborate. Here also same, elaborate, and we have to give the top level module name, not the file name. Okay, whichever this thing you gave in set design, right, exactly the same thing you have to give here also, the same module name, and enter. And give you all these messages, and then here also you will see that something has come here for the full adder. And once this is done, you get that picture, your synthesize space to mapped. There is no option for giving another design name or anything. Synthesize to mapped, enter, and then that's it. It is the final synthesis. Now here we can generate the power area timing reports, but also we can see this is a netlist. Okay, this is a netlist that is different from your Verilog file. This is your Verilog file. It has 1 2 3 4 5 gates are there in your Verilog file. If you see this one, it has only 1 2 3 gates. So it has actually reduced the, it has taken your Verilog file and done something called as logic minimization. It has reduced the logic to a simpler expression, and it has able to implement your 5 gate Verilog file in just 3 gates: XOR, one AND OR gate and another XOR gate, and this is called as a netlist. Okay, and also of course we can generate the power area and timing report. Power, will get the power total in nanowatts, and report timing, what is the total delay for the full adder, it is 276 picoseconds, and report area, what is the size of the full adder, it is 17 units. Okay, so this is the output of front end design, these numbers along with the netlist. And let us do this once more. Okay, for the register, so the tool is such that we cannot do the synthesis twice for two different designs, or even the same design two times. Okay, once you finish one, you have to press exit and come out of the tool, then go back to setup.g and change it to the new module. New module is shift register .v, and the module name is shift, R was capital, register, it should be in exactly the same case. Okay, see this, R capital, so we should also give it in the same way, shift reg, not register, and save it. Now go back to the terminal, start with RCGUI. Okay, and then same steps. Okay, so it is reading, you can see if it is reading the correct file. Sorry, so I forgot one step. What was the step? Set attribute library dollar library. Yeah. See, there's a design could not find a HDL design, so something went wrong. So we have to check all the this thing. Shift reg is the name of the module, and here also it's shift reg. See, no, nothing has come in the GUI, so something went wrong. Let us try it again from the first step, because we missed that step, maybe something went wrong, so we'll try it again. The names are fine. Okay, so let's try to elaborate. Again, it's giving a mistake. Okay, let's see what we have done wrong. Okay, so we have done a mistake here. We have given the wrong file here. Our file name is shiftreg.v. The other module that was there in the this thing is the shift register. So there's two files which have similar names. I was giving the wrong file, so we will exit again. Okay, setup.g, shift reg is the module name, shiftreg.v is the file name for my file. So save this and save this also, and start from the first step. Okay, Okay, so this time it's reading the correct file name. Okay, and then elaborate. Okay, so done elaborating design, and you should see it here also. Now synthesize -2 mapped and completely changed. This is the new design. You can see what are all these gates. This is a gate, this is a AND or invert gate, this is a D flip-flop, this is another AND or invert. They're all mostly flip-flops because this is register, this NOR gate, etc, etc. Okay, so if you want the exact this thing, how do you get it? Write _HTL, so you can get the netlist. And we started off with a Verilog code in RTL with the always statement. All that is gone. Pure combination, pure structural code with only gates being instantiated. These are all D flip-flop. This is OR and invert gate. This is AND or invert gates, and there is some NOR gates. Okay, so this is the timing report. 564 picoseconds. Report area 186 micrometer square. Report power 3308 nanowatts. So quite big, quite large for such a small design, right? So this is the synthesis for the shift register, and these steps are identical for any design. Okay, clock, without clock. So only difference you will see is here there are some more things here. Timing slack, it says unconstrained. If we had more time, we would talk about how we can tell the design to synthesize along with some timing constraints, but we are not going to do that. So this is the only difference that you will see in the reports. Okay, so this is the end of the synthesis steps also. The next one we will look at the transistor level circuits. Okay, thank you.